So the kind of question that we're looking at is that we're interested in is social interaction. So by social interaction, we mean, like everybody means, interaction which are not mediated through markets. So essentially, this is environment where the action of the agents end up depending, after the maximization problem, the action of an agent ends up depending on the other agent's actions. This kind of environment, of course, in some sense, by definition, have an externality built into. And so they're kind of interesting in general to think about social environment, but of course, it's crucial that, in some sense, you identify the externality. So for policy reasons, these environments are important in the sense that, of course, if the action of agent A depends on the action of agent A plus 1, then you might just have to act on agent A plus 1 and you get... which way?
Because the camera is...
Okay. This way.
Here.
Oh, here. Okay.
Okay.
Okay. So for policy intervention, of course, there's kind of a domino effect. That's what's important in this environment, in the sense that if the action of one agent depends on a mean or some action of some of the other agent, you act on one and you have effects on all the others. So this is sometimes called social multiplier. Okay, so this kind of environment have been claimed to be important in many dimensions. People who looked at crime will see something. I don't remember if today, if Zanu is going to talk about this, or they've been applied school attendance, out of wedlock birth, smoking habits, women in the labor force, and all sorts of job search referrals, education, many kind of applications. So I'm not going to I'm not going to look at any specific application today. I'm going to develop some theory results, some theoretical results. I'm going to think about some, hopefully, rather general class of these economies and give you results about existence characterization. But I also want a little bit to talk about identification. As I said, and I'm going to give you a few results or hints of results about identification. As I said, the identification problem here is it's crucial. In some sense, it's very important to understand, again, for positive but also for normative reasons. It's important to understand if this social multiplier effect really is at place or is it not. Of course, this problem is cursed by a fundamental identification problem that was identified by Mansky, which he refers to as the reflection problem. Essentially, the problem is, this is just a simple example of what he was saying. If you have a linear model where the action of agent A, little a, in group big A, depends on the mean xa, x big A, depends on the mean of the group, then, of course, if you have data on means for different groups, there's no way you can identify beta 2. Okay, so essentially beta 2 is what we need to identify. Beta 2 is in some sense a measure, or if beta 2 is positive, then we have a social multiplier. Okay, so that means we have an externality, that means we have possible different policy implication. Okay, so this is the classic problem. So identification fails in this case. There are many ways, there are different ways that people went to try to identify these models. One is, sorry, I have to go back and forth, otherwise it's too small. So the identification problem, it's of course comes up crucially in the linear setup. So one thing that people have done is they've looked at nonlinear environments. So for instance, Brock and Durloff have a logit model with distributional assumption, and in that case they can find identification. So what we are going to do today is, in some sense, for most of the examples at least, we're going to stick with the linear environment. But we're going to specify structural form of interaction in the sense of we're going to think about local interaction. So we're going to be a bit more precise on what is the form of this interaction, of this externality, on the space location, where space, of course, is to be interpreted abstractly It might be really location, but it might be just a dimension where networks arise. So the whole, in some sense, the whole idea is if we put this kind of structure, this local structure, into the model, the question is, does this help identify social interaction or not? In some sense, thinking of the action of one agent as depending on the mean of the action of other agents is a reduced form. I mean, in some sense, you might want to, in some issues, you might want to interpret that literally, but more generally, you think of that as a reduced form argument. It's just saying that the action of one agent depends on the other guys. So I want to get a bit more structure. I mean, it's of course not just me. A lot of people have done this, but you want to get a little bit more structure in terms of how does this really, how this action of one agent depends on the other agent, and see if that helps you identify and characterize the kind of behavior in these economies. Okay, so this is really what we're doing. We're going to look at static and dynamic economies with local interaction, and we're looking at existence and uniqueness. Most of the time, the two questions are the same in the sense that we're after uniqueness. We're going to look at characterization, and we're going to talk to concentrate on a linear example. And in this linear example, we can discuss a bit more identification and other properties. Okay, so I'm going to go quickly through the static economy, where there is less of a contribution, at least a theoretical contribution, and then I'll give you an idea of how I can look at dynamics in these economies. Okay, so the kind of interaction that I'm looking at, it's going to be very simple. In many sense, this can be generalized. In many dimensions, this can be generalized easy, but just to fix ideas, I'm going to have a location which is a line. I'm going to have an agent 0, agent 1, agent 2, and I'm going to have an environment where the utility of agent 0 depends on the utility of agent 1, and the utility of agent 1 depends on the utility of agent 2, and so on. Of course, I can make this, not of course, it's not that trivial, but I can make more interesting, I can think about more interesting forms of local interaction, and I'll be happy to talk about this, even though I won't mention in the talk. So this, I'm going to think of this location as the number of agents as infinity, because I'm going to need to be talking about large numbers and things of this sort. Okay, so the environment is each agent A. I'm indexing agent with the name A. He'll take an action XA. He'll be hit by shocks. These are preference shocks, theta A. These are IID with a known distribution. Again, the interaction is as I said. The interaction is as I said, so the agent A interacts with agent A plus 1. The utility, as I said, it's the manifestation of interaction, so the utility of agent A depends on its right neighbor, and of course on the shock. Okay? So I'm going to, just to fix ideas, I'm going to look at the case of complete information, where all the agents know all the possible shock of everybody else in the economy. Of course, this is a very strong assumption, even though it's the assumption that everybody uses in this literature. It's very, it's very strong, and what we do in the paper is also relax this and allow for a local dimension of information too. Because if you are in an environment where you think, again, the interaction is local, you might want to think, you might want to assume that what agent A observes, for instance, is the shock of agent A plus 1, if that's the one who affects him, but doesn't see, or maybe a couple of agents, but doesn't see the whole direction of the shock. So that's easily doable. Okay, but for purpose of the talk, I'm not going to talk about this. Okay, so let's define an equilibrium. A policy function maps the whole configuration of thetas, by which I mean, well, in fact, only the right end. So agent, to fix ideas, agent 0, his policy function, his action x depends on all the realization of thetas. To his right, that object T is just a shift operator. So TA is starting, if you start from 0, agent A, let's say agent 2, looks at all the shocks, 2, 3, 4, 5 included. So an equilibrium here is defined by a fixed point of that form. So G of theta is the policy, is the policy function of agent, let's say agent 0 in this case, it's the Argmax of the utility. This agent chooses x0 and takes for given the policy function, the same policy function at the fixed point of agent 1. The policy function of agent 1 as an argument the whole configuration of theta, but starting at 1. Okay? So you can find, this is a technical slide. So the first result is relatively straightforward. Essentially, this gives condition for existence and uniqueness for that fixed point to be a contraction, and really that we are asking for a bunch of technical issues. We require alpha concavity and a bunch of things, but essentially what the conditions say, the condition for existence, what they say is that the utility, this is xa plus 1 theta a, they say that the cross partial dx a plus 1, this must be less than the second derivative. Right, so essentially what the condition says, this is the condition for a contraction, it's sometimes called moderate social influence. So what that means is essentially your action, your policy function depends on your own action and depends on the action of the neighbor. It must depend on your own action on your own shock more than it does depend on the action of the neighbor. Okay, so the local interaction effect cannot be too strong. If it is too strong, then you're going to have, in fact, multiple equilibria and phase transitions. So if that is not the case, this is a general way of writing that condition, not very important. If that is the case, then we have existence and uniqueness. Okay, so a typical example, our baseline example actually, it's one with a quadratic economy, like there, where essentially the agent hates, he's choosing action x a, and he gets this utility from his action being far from theta, his own shock, and far from the action of his neighbor. Okay, so in this environment, so that's why we call it a local conformity model. In this kind of a model, then it's easy, it's obviously very easy to solve in closed form, and what the policy function look like is a weighted average of everybody's shock, which declines geometrically with distance. Okay? So then in this kind of economies, well, there's a bunch of course, it's very simple economy. There's a bunch of things you can do that people actually do, which is you have implication about the variance of the action, the variance of different configuration. You can look at clustering of actions, and so this is you can get some interesting comparative statics. Okay, so the important thing in some sense here, go through. So this object over there, that's variance over A over variance of x bar. X bar is some measure of a mean action. So that object is what is usually referred to as the social multiplier. Okay, so essentially the whole point of this is you can have a closed form equation for the social multiplier. You can do comparative statics, and you can, in principle, and we see the important point is, can we really identify? Okay, so this, as I said, this economy is very simple, very straightforward. The crucial point here, though, that I want to stress a little bit is identification. As I said, one of the reasons why we went into thinking about local interaction is because if you think about only global interaction the way Mansky was doing, you have a fundamental identification problem. Okay? So in some sense the question is, if I go to local interaction, can I really identify the social multiplier? Okay? I'm putting more structure into it, I'm requiring individual data. Does that help? Okay? So at first it might seem no, in the sense that look about those two model equation number 3 represents my model, the local interaction model. That's the first order condition of the quadratic utility version of the model is exactly that. The action of agent A, it's a weighted average of theta A, its own shock, and the action of the neighbor. Okay, so that model is really, if you look at, so another possible model is in fact a model where the action of agent A just depends on a random shock, RA. Okay, some kind of random shock, which is A, so with no local interaction effect in terms of actions. Okay, where I do not look at my neighbor, I just have a shock, and that determines my action, but where the shock is correlated over space. Okay, so that's an important case, because it might seem strange that the shock is correlated across space, but that really means selection in some sense. So if you think of what the shock R is really preferences or the environment that the agent faces, and for it being correlated across the local dimension essentially means that similar people live together. Okay, so it's an abstract way of measuring an environment where you have sorting and selection. Okay, so in fact it turns out these two models are indistinguishable from unconditional variances and covariances. Okay, so these two models have the same variance and covariance structure. In other words, you can, given beta 1 and beta 2, you can find an eta and rho such that the two models generate the same variance and covariance structure, where covariance and incovariance across different agents on the location. Okay? It turns out, though, and this is really, so for instance, this is what Glaser and Schenkman do. They assume the model, the reference model, when they look at crime, they assume that the reference model is 3, and they compute beta 2 looking at that covariance of xa plus 1 over the variance. Okay, so that's identified in the model, that's beta 2, so they estimate that and they look at beta 2. Now, again, there is another model that could actually generate that same covariance structure, which has no local interaction. Turns out, though, that there is a way, right, with that covariance structure. So it turns out that there is a way to identify this model. This is just in the quadratic case, but it gives you an idea, a general idea of how you can do this. Okay, so model number 3, equation number 3, which is my local interaction model, has the property that the local interaction is through the action of the neighbor. Okay, so if I know the structure of neighbor, of course here I'm assuming that I know the structure of neighbor. So if I know the structure of neighbor, if I look at conditional covariances of the form of that form, where I look at the covariance of action A with the covariance of actions of the action of agents outside of the neighbor, conditioning on the action in the neighbor, that covariance is 0 in the local interaction model. On the other hand, that covariance is positive if there is a long correlation structure in the shocks. So this is a very specific linear environment, and these are two very specific models. But the intuition of this, the intuition that this way you can, in general, identify this model is more general, in the sense that essentially the local interaction model generates long covariances. So to generate these long covariances without local interaction, what you need is long correlations in the shock. But then, by long I mean long in the location. But then the local interaction model generates conditional covariances of this form, which stop after a while. That cannot be the case in the correlation model. Okay, so I want to take from this that this class of model is actually interesting, and it is actually helping us identify social interaction. Possibly, of course, the trick here, the important element here is that I'm possibly identifying the parameter of interest under, in some sense, the assumption that the structure of the interaction is known. Okay, so if I start not really knowing what is the structure of interaction, then of course the problem is much more complicated. Yes. So as I said, we can have the incomplete. We have the incomplete information case, but I don't think I have time to discuss that. Okay. So let me look at dynamic economies. Okay. So asymmetric equilibrium of the static complete information economy, in the case in which it's not linear, can be written in that form. Okay. So xa is a function of theta A and xa plus 1. So what has people done? Well, Larry Bloom actually, he's not here, but he's one of the early contributors to this literature. So what people have done is they've essentially used results from the statistical dynamics literature, the statistical mechanics literature, I'm sorry, in physics. There's a large literature about the properties of dynamical systems of that kind. So they've taken the static model and they've added time, okay? But they've added time in a myopic ad hoc way. So the idea is every agent A at time t plus 1, so there's a stochastic process which decides which agent decides when, takes an action when, and then when this agent is taken to the side, he looks back to his neighbor. He looks to his neighbor one period before, or at that moment, and takes an action which is completely myopic, which only depends on what his neighbor is doing now, what the action of the neighbor is now, but without any understanding of forward-looking aspect on his own side, because the agent A will be asked to the side again, and without no forward-looking aspect with respect to the decision of his neighbor. Okay, so it's a completely myopic. The reason why people have done this is that there's a large literature out there which characterizes the dynamics of those objects. Okay, again in physics, in physics though, these models are used to model the dynamics of particle systems, and particles are not very forward-looking. So if you think of those objects as agents, we want to think about rational expectation. So what I'm going to do is I'm going to look at this model, but I'm going to do it our own way, okay, with rational expectation. So I'm going to look at as a particular example. I mean, a particular model, but again, what I say is much more general than that. Okay, so I'm going to have an agent at time t, agent A at time t takes an action, same, he has a random shock, the same, now there are indexes t all over. The local interaction is the same. By the way, in the static case, I could have beautiful local interaction networks and stuff, and a lot of what I'd said went through. In the dynamic case, I don't know. In the dynamic case, I have existence results for this simple interaction, but most general cases, that's much harder to look at. So I don't really know. So the one assumption that I'm going to make, this is though not very important, is I'm going to say that an agent at time t observes the whole configuration of actions the period before. So now this is at a time t. There is another line at time t minus 1. Okay, so this agent is going to observe the whole action, the whole configuration of actions yesterday, but he's only going to observe his own shock today. So I'm not letting him observe all the shocks, but that I could do. It's just that it gives me another infinite sum that I don't want to carry over, but that is not a problem. So in this sense, it's incomplete information. This agent here doesn't know what the shock of this agent is at time t or anything else, but he can make a forecast what the action of this agent is based on the action of this same agent that the period before and everybody else. Okay, so I'm going to have a discount factor beta. Okay, so how do policy functions in this economy look like? Policy functions have that form. So the policy function is G. So again, it depends on the whole configuration. In fact, what I'm assuming here, I'm looking at macro-perfect Nash equilibria, macro-perfect equilibria, so only payoff relevant state variable are in. This is an assumption, a simplification, but so essentially agent 0 will look at all the past actions of everybody on his right. He will not use actions of people on his left. He could. I mean, in principle, you think of those as sunspots or things like that. So we're not looking at that. So we're only looking at equilibria where what the agent does is he's looking at action on his right. So the action of agent A depends on all the actions of the agents to his right yesterday, and that depends on his own paper. Okay? So given that, I can construct essentially that big pi G there, it's a transition matrix. So if I assume that every agent uses a policy function G, then I can construct that by simply taking products, I can construct a transition matrix of this whole list of configuration. Okay, so given a list of actions, a configuration of action at time t minus 1, this gives me probability over different configuration of actions at time t. Okay, this is a kind of a nasty object, but not too bad. Okay, so let me just give you. So the first thing I'm going to do is I'm going to show. I'm going to give you conditions for existence here. Let me just give you a hint of the way this goes, and then I go to some characterization issues. Till when do I go? Remember? 10. Okay. So the optimization problem of agents, let's say agent 0 is that object over there is maximizing the expected utility at time 0 plus a present discounted value of utilities from that point on. Of course, the operators with respect to which it takes expectation depends on G, which is the policy function of all the agents to his right. Okay? I can write that problem recursively, and this is what it is down there. So VG is the value function, given that all the agents to the right of agent 0 use policy function G. That's why it's indexed by G. Okay? So it's easy to see. So the first thing one does is one shows that that policy function is, that value function exists, it's directly concave, there's a unique policy function which comes up of this problem. And I denote that policy function G hat. Okay, so that is really my best reply map. So given a policy function G, through this problem, I compute a policy function G hat. Okay, so not surprisingly, my equilibrium is a fixed point of this map. Okay, so I feed in a G to the right hand side, I get a G hat, and I keep iterating until the G hat is equal to the G. When I find that, I have a fixed point, and I have a symmetric macro-perfect equilibrium. Okay, so can I do this? The issue here, the issue, of course, in some sense is in which space you look at. But really, the important issue is being able to have a bound on x b t minus 1 for b greater than 0. The whole point is there's an infinite list of partial derivative of the policy function G with respect to all the actions of all the agent to his right. Now, these partial derivatives must be summable, okay? And that's fine, but the whole point of the whole difficulty, or the whole point of the existence theorem is you have to find a sum. So these things are summable. You sum them with respect to B. Okay, and so you have to find a sum of, you have to find a sum of these things, which is such that it's, in some sense it's the maximal sum. So that if you feed a policy function G to the right hand side, which has partial derivative with sum to C, then any policy function that you get on the left hand side is going to have a smaller or equal sum C. Okay, so if you can find that, then you're done. Okay, so that essentially means you're looking to space of Lipschitz function where the definition of Lipschitz continuity kind of depends on this C. Once you've done that, and that's the hard part of it, then you're done. Okay, so it turns out that you can do that. It turns out that you can do that. The trick to do it is using some results that Manuel Santos had of differentiability of policy function, because that helps you bound these things, having an upper bound of this, so having conditions on the utility function such that summability there is guaranteed. Okay, and it turns out really that the conditions on the utility functions in the dynamic case are not very different from the ones in the static case, in the sense that you require conditions which tell you that the derivative of the utility function with respect to the agent of your neighbor is smaller than the second derivative, the second derivative utility function with respect to your action and your neighbors must be smaller than the second derivative utility function with respect to your own action. Okay? So again, the policy function must have this property that it reacts to your shocks more than it reacts to the action of the other agent. To the action of the other agent. Okay. So once we have the existence result, well, then again we can have some sort of stability result. We go through this. So we have properties about this Markov process, which maps configuration of action at t minus 1 into configuration of action at t, and we'll know under some condition that it's going to have a unique invariant distribution. Okay, so let me look at the quadratic case here too. Okay, so the quadratic case, again, we're having a utility function of that sort where the agent hates being far away from his own theta, hates being far away from the action of the other agents, but also hates being far away of his own action yesterday. That introduces some sort of habits into this economy or adjustment cost, whatever you want to call them. So for this economy, it's easy to see. I mean, it's not that easy actually, but you can see that the policy function is actually linear, but it has that form. Okay. So once again, it's a weighted average. It's a weighted average of the action in the past. Of course, it depends on your own action in the past, depends on your own shock today, and it depends on all the action of your neighbors in the past, all the neighbors to your right. But that CB now is not necessarily geometrically declining. It might be, but we don't know. We were unable to prove. So again, now the issue here, actually the reason why we got to looking at the static model was because we first looked at the dynamic model to try to understand the identification issue. Okay, so the same kind of issue, the same kind of result. So in the linear environment, that's the form of the first order condition, and then again, somehow the question is, can you find a process R? Can you find a process R which is correlated across time and across agents, which generates the same variances and covariances that the process number 5 up there generates? And the answer once again is no, at least in this linear case. The answer once again is no, because, and once again, the way you identify this economy is by looking at conditional variances, conditional covariances, where the conditioning now is across, it's across location, but it's also over time, right? So again, adding dynamics, of course, this adds data too, but adding dynamics adds identification restriction to this economy, fortunately, hopefully, given the complication we had to go through, but adds identification restriction in this economy, so in principle, that's helpful. Okay, so let me say just a couple of things, a couple of more things about this economy. So one of the motivations for looking at the dynamic economy, as I said, is because we wanted to look at rational expectation equilibrium, and we wanted to compare this with what the literature had done before, which is to look at myopic economies. So we can kind of have a sense of one of the things that we wanted to understand was what's the effect of requiring rational expectation on the policy function. Does it make this agent more reactive or less reactive to the local interaction, right? In principle, if you think about the question, it can go either way, okay? You might anticipate that the agent is moving tomorrow and then move earlier today, so giving you an extra local interaction, or the other way around. So we kind of wanted to have a quick simulation to have a look at this. So there's two dimensions. There's two dimensions of myopia in the classic, in the standard way people have looked at this economy. One dimension is the most myopic case, which is the one that people have looked at, is you're acting at time, agent A is acting at time t, not knowing, not realizing that he himself is going to act again, and that the agent, his neighbor, is also going to act. The second case is, it's a bit less myopic, but it's still myopic. You realize that you're going to act again tomorrow, but you expect your neighbor to be stuck in his choice. Okay, so what we're doing now, we're looking at a two-period economy, just because we actually can. We have solved algorithm to simulate, to find the policy function of the infinite horizon case. But when we have done this, we haven't done that yet. So we looked at a two-period version of this economy, which we can solve by hand. And we computed the policy function in three cases: the completely myopic, the halfway myopic, and the rational expectation. And then we've used simulations, just throwing in, I mean, it's not really simulation, we've just thrown in parameters to see what happened. Okay, so some of the results are this: when the local conformity is not the predominant component, so the preferences are alpha 1, alpha 2, alpha 3 equal to 1. So all the three dimensions, your own action yesterday, your shock, and your neighbor action enter with the same weight in the utility function. In this case, well, the number of neighbors that affect in a significant way the action is the order 7, 8. When the local conformity is predominant, the number of action is much larger. Okay, but that's not very important. So the point in the simulations, what we find is that the policy function of the myopic agent overestimates, with respect to the policy function of fully rational agent, the dependence of equilibrium action. Okay, so if you're rational, you end up putting less weight on your neighbors than you do if you're not rational in the way we're postulating. And this effect, whatever it's, again, we'll have soon, but we don't have a full calibration of any particular environment, so it's hard to have a measure of this. But when local conformity is predominant, essentially, if you're not rational, you only impose weight on your neighbor. If you're rational, you impose weight on everybody. But in our parameterization, if you're myopic, then you put weight 0.8. These are the weights sum to 1, so it's a huge weight. These are all the policy function are convex combination of the arguments. So in the fully myopic case, you put weight 0.8 on your neighbor, while in the fully rational case, you put weights on everybody to your right, and the sum of all the weights is 0.29. Okay, so 3 times different, whatever that means. But this is an indication that this element is important. Now, I mean, of course, it requires simulation. So I'm almost done. Yes. So now we have an algorithm to compute policy functions, which essentially is the iteration procedure. That it's our fixed point problem. And let me say a couple of things about the extension, and I'm done. So, as I said, in the static economy, I have no real problems. In thinking about more interesting social structure. Okay, so in particular, I can think of the one-sided interaction that I've looked at. They are actually extremely restrictive, of course, because they restrict very strongly the form of strategic interaction. There's no, if A has an effect on A plus 1, it's not the case that A plus 1 has an effect on A. Of course, as soon as you have neighbors which go both on the right and to the left, you now have this cross effect. This change the structure of the problem dramatically, but in the static case, you can compute it, you can actually characterize, in the quadratic case, you can characterize the solution, and there's a lot of things that you can do. In the dynamic case, I don't know that this essentially adds an extra fixed point problem to my fixed point problem, and I'm not really sure I can deal with it. I mean, I haven't tried that hard to do it, but it's certainly not completely straightforward. The other dimension that one can look at, and we've done in the paper, is to look at both local and global interaction. Okay, so to have an environment where, like this one, but where the action of the agent doesn't only depend on its neighbor, but also depends on some aggregate measure of the action of the economy, the mean or the variance or something. So in this kind of economies, if we impose enough condition, like we've done, on the utility function, actually a law of large numbers, holds. In that case, essentially, you can look at this economy local and global interaction without particular without particular problems. Now, one last thing, in these economies, essentially, I've kind of hidden it, but we are looking at contractions. We are having existence. Together with existence, we are having uniqueness results. This is important, but it's also very limiting. So the conditions for existence are strong because we essentially require uniqueness. Now, there are a lot of extremely interesting stuff which happens if you relax this. For instance, very important is the case where the low black number doesn't hold anymore. Okay, so if you have strong interaction enough, then that what happens is what it's usually referred to as a phase transition. Okay, so it's a phase transition in the space of probability distribution over the whole configuration is an environment where the low black number doesn't hold anymore, and the mean action is not has not zero variance, but it actually has a positive variance associated. Okay, so a lot has been done in physics with this case, and it's of course very interesting, but we have completely held that up. Of course, it's very hard to think about how to go and estimating this process if you allow for phase transition, but of course that's also very interesting. We haven't done that. No, thank you.
Okay, thank you very much. The discussant is Itzik Zilka. Itzik? Ah.
It's here, I believe. I'm not sure how it works, but
Is it on?
it doesn't seem to be on.
Yeah, I'm sorry. I don't see so well.
Oh, here.
Oh, yeah, right. Okay. רגע, רואים את זה או לא? כן. מה? הלכותי? איך הפוקוס? איך עושים פוקוס? Okay. Can you see it? Sorry, I didn't take that into account.
It's better? It's better? Okay. Yeah.
אוקיי.
אתה רוצה זה?
לא, זה בסדר.
לייזר?
לא צריך. Well, first of all, I really like the paper, even though it's technical and even though the paper uses very strong assumptions in order to generate those strong results that Alberto has mentioned already. I think the main contribution of the paper is the dynamic case, and not so much the static case. And moreover, I think the examples are very instructive and very important in this case, and probably the examples have motivated also the whole paper, I believe. Now the contribution to the existing literature, and there is a vast literature that deals with the issue of social interaction in recent years, as you could see from the references to this paper, is that the paper actually deals also with complete information and incomplete information, where Alberto decided to ignore, to some extent, the incomplete information case. and both are local. The complete information and the information and the interactions both are local in this model. Now the dynamic model, which is where the main contribution has been done, consider the deviates from the myopic case that has been extensively discussed in the literature. And agents, when they choose their actions, they basically take into account, they are forward-looking, and they take into account how their action would affect their neighbors, and they take into account also the past as well as the future, expected future. I think that the incomplete information produces some interesting results, and when I say incomplete information case, I mean that you really take into account only a finite number of neighbors and not the whole sequence. You see, as you look at this case, you're basically looking at one-sided case, but you don't take into account the full. You don't take into account the full number of people on this side of yours, but rather only a finite number, let's say 1, 2, 3, or n, finite n, let's say. And in this case, the incomplete case results in sharper and I think also from bounded rationality point of view, I would say that the incomplete information case is the more interesting one. And I would put more attention, I would give it more attention to this case than it's done in the paper. Even though working with the shift operator, it is much easier to take infinite sequences. It's clear. Also for existence, I think, as well. But I would give it more weight because the results really differ. Now let me say this. The existence and uniqueness results are strong and very nice. But on the other hand, they require strong assumptions, and the strong assumptions are sometimes too strong in some way. The one-sided interaction is an important feature of the model. It is not going to be easy to relax this assumption because basically they eliminate some strategic coordination and they eliminate multiple equilibria as well in this case. Assumptions about preferences here. The alpha concavity, there is an assumption of alpha concavity and assumption of Lipschitzian constant, uniform Lipschitzian condition. But the two are tied to each other. The constant that appears in the Lipschitzian condition is not independent completely of the concavity, alpha concavity that you're using, and therefore I think that tying these two conditions together makes the assumptions together much stronger than otherwise. Okay. Now, I'm sorry, yeah. The dynamic framework also assumes IID assumptions about the shocks of the individual himself and the others, and I think that this is, in this case at least, seems to be too strong. Another assumption that I find this way, thank you. Another assumption that I find to be strong is that agent needs to observe the entire actions profile. And once again, I think the amount of information you need to put in there is very tremendous, basically. Even if you work in a stationary environment, still the observation is of the entire action profile of all the agents to the right of this given agent. And I realized that the policy function that you derive, and remember, in this case, the paper derived the equilibrium is basically symmetric Nash equilibrium. And therefore, the result is strong. And in the examples case, you have an explicit solution, closed form solution. And therefore, you need such strong assumptions. But on the other hand, from practical point of view, this is a strong assumption. I would recommend reading the examples first. Whoever reading the paper, I would recommend reading the examples first, because the examples are very instructive and basically gives you an idea how the results in general work and what are the difficulties also. When you look at the static case, where there is no habit formation in the first case, only the conformity, you find that conformity does not generate a variance multiplier. In the incomplete information case, the conformity dampens the variance, okay, of the mean action. Also, the social multiplier, which is defined in this case as a ratio of the variance of individual action versus the variance of the mean action, is larger in the complete information case, which was mainly discussed here, versus the incomplete information case. And this is an interesting and probably not so intuitive type of result. In the dynamic case, and I consider the main contribution of the paper to the dynamic case, given the vast literature that exists, we find some very interesting observations as well. Especially dealing with the rational expectation case, which basically, as was mentioned here, gives a different result from the myopic case, and creates at the same time a lot of difficulties. And analyzing the rational expectation equilibrium here is not that simple. Even in the example, existence of this equilibrium and the closed form solution requires a lot of work. Now, in the example, you could see that agents take into account, each agent has to take into account how his own action, first of all, he has to take into account that he's going to act once again, and not just today, okay? This is already a big difference. The other difference is that his own action will affect the actions taken by his neighbors as well, where in the myopic case, this type of calculation does not exist at all. And this makes the analysis and the derivation of the policy function, which is a linear, in this case, in this example, harder to achieve. Now, the existence of symmetric Markov equilibrium here with a linear policy function has been derived due to the quadratic form of the utility function, of course. And I wonder how if you modify a little bit the preferences, how the linearity, at least, of the policy function would survive or not survive. It's not clear. So it may be that this example is really a unique case but you said that you have also additional results that...
The existence result that it's in the paper that I gave today is not in the paper. So existence is not a problem with more than utility function. Of course, linearity is not.
The linearity, yes.
Comes from the quadratic.
And a lot of the results that characterize this example may not hold if you don't have linearity. Yes, right. Anyway, some of the unique results that you derive from this example, the closed form solution, is that when the ability to re-optimize a date t plus 1 results in a better match of the arguments that vary over time. This is one thing. Rational expectations. The optimal choice reduces the dependence of agents' actions on local conformity. In this example, you have local conformity as well as habits. And in this case, the weights on habits versus local conformity vary in the myopic case versus the rational expectation case. And rational expectation results in putting less emphasis on the conformity and more emphasis on the habits. Now, Also, if you look at the rational expectation results, in this case, you find that since all agents have information about the past, and they take the expected expectation action of their neighbor, okay, neighbors, I mean all the bees to the right, this guy, then you find that more weight is put on the mean shock, okay, the mean shock versus the history, versus the past actions. If we try to learn something from this example and to ask what would happen if we really try to generalize these results, one would ask, first of all, how would the result look like when you have incomplete information? And since I think the incomplete information case is the more interesting from bounded rationality point of view, from other point of views, and the amount of information you have to feed a decision maker, okay, then I think it would make sense to take this example and to try to answer how incomplete information would affect all these results. In general, I would say that you needed the strong assumptions here to generate this type of equilibrium, existence and uniqueness, okay? But on the other hand, it is the examples that really gives the insight to the readers. And it would be interesting to, at least for the example, the second example in the dynamic case, to try and give us an idea how the example can be extended in various ways and how some assumptions at least can be relaxed. For example, the incomplete information case is the interesting case that I would like to see resolved for this example. But I think that the contribution of the paper to the literature is interesting, especially the dynamic framework that's been used here. The existence results are not trivial at all, and therefore the question is whether the insight we derive from the example are really robust. And I don't know. I couldn't answer this. But I enjoyed reading the paper.
Okay, thank you very much. The floor is open for questions and comments. Yes.
Yeah, well, I guess that's a clarifying question. I understand what's going on in the static model.
Yeah.
So I understand what's going on in the static model. In particular, I understand that you got uniqueness.
Yeah.
In the dynamic version, so when you're looking for this symmetric Markov perfect equilibrium, both in your in the statement you presented here and in the paper you prove existence. You don't talk about uniqueness.
I don't have you.
And my intuition would be that there is no reason to get uniqueness. But now one of the reasons why I expect not to be uniqueness is that there might be some spot in this kind of stuff. And it seems to me that this situation in which what you do today depend on what does you. Did you explore this kind of situation? In particular, at some point you alluded to it. You were saying when you look at equilibrium in which at any moment when you look at the past, you only look at the past behavior of the people who are relevant. And in principle, you could as well look at people who are relevant, but then it would be something. But my gut reaction would be there might be equilibrium that depend on everything, including the irrelevant ones, and this would be typical sense of equilibrium. So the technique you're using is sort of reminiscent of the sense of literature.
Should I take answer now? So let me answer. Let me answer immediately. Yes. So we're looking for equilibria where the policy function only depends on the action of agent to your right. So that means that by construction we're looking at equilibria